So next up we've got Sinead Williamson from Apple.
Great. You can maybe move that. Awesome. So I'm from Apple Machine Learning Research, which is Apple's pure research organization. If you want to know how uncertainty goes into Siri or other Apple products, your guess is as good as mine. I'm just going to be talking about our research areas, which is informed by what the product teams does, but kind of orthogonal to it. And what I'm going to do today is give an overview of a variety of projects over the last year that people in our team have been working on. Now, some of this is work that I've been involved in, some of it is work that I haven't, but is really cool, so I wanted to share with you anyway. I'm going to put an asterisk top right on slides that I was not involved in, so that you know I can still answer questions on that, but I'm not going to be able to go into like deep theoretical proofs on that. All right, so you are interested in machine learning, you're interested in uncertainty, and you want to put these together. Where do we start? Also, I should say, when I'm talking about machine learning today, I'm mostly talking about large language models. Some of it generalizes beyond that, some of the calibration stuff is more general, but most of the time, it's going to be LLMs. First thing we need is a way of pulling out uncertainties from our model. These first few slides are going to perfectly match the 3 workshops that we had, and I did not intend that. So this was kind of like the topic of the first workshop here. We want to get numbers out. And people have done a lot of work in this. Some of it at Apple, so I'm putting all of our references at the bottom, most of it beyond Apple, of assigning numbers to statements that LLMs make. Right? So you can look at sequence likelihood, which looks at the logits of a generation to get a probability. You can look at semantic entropy, which samples from a distribution, clusters them, and estimates the entropy of the categorical. Verbalized uncertainty, which is just asking the LLM how uncertain it thinks it is, and so on. Okay, so we've got a lot of tools from taking the output of an LLM and giving out some number that maybe represents our uncertainty. But we don't care about this in a vacuum. Workshop 3. We care about what we can do with this. Right? So we want to use these numbers or measures in order to improve our interactions with LLMs, in order to build better models, in order to use them in downstream tasks. So this could be similar to the last talk in gathering useful information. So at Apple, we're using uncertainty quantification LLMs as a pathway to doing basic experimental design with LLMs. It could also be, for example, in fairness. So some of my colleagues are working on how you can use uncertainty as a measure of evaluating the fairness of LLMs, loosely by looking at if men and women have similar uncertainty profiles, then that's good. If the model's really confident on men, really unconfident on women, that's bad. Workshop 2, in order to do the applications, though, you need to have an alignment between these two things. Now, alignment is a massively overused word in machine learning. So what do I mean by this? So in this context, I mean, if I want to use a measure of uncertainty, I need to know what it's trying to tell me and whether it's actually telling me that. Right? So I need to know that, or trust that the number that I'm getting out is actually the number that I think it is. So first off, what do I think it is? There's a lot of views of what a probability could represent. Bayesianists and frequentists have argued for a long time about this. But a typical assumption is that the uncertainty is a measure of how likely the model is to be correct. Right? I ask it a question, gives me a number out, and I'm somehow going to take that number to mean how likely is it to be the right answer. We've got a number of approaches for measuring whether that number actually makes sense. Okay? We can look at various notions of calibration. So for example, confidence calibration asks, if I take all of the cases where it said I'm 90% confident and look at how often it was right, is it right 90% of those times? If so, it's a meaningful notion of correctness. We can also look at things like ROC, which measures how well does the model's confidence align with its correctness. Right? Does this uncertainty measure act as a good predictor of confidence? And these are both well understood notions of validating uncertainties, and you see them a lot in, for example, classification. But they both get a lot more complicated when we're working with LLMs. And the main reason for this is because we no longer have neat boxes. We no longer have K categories where we know exactly what box we're in, and we can assign a number to each box. We have language. Language is messy, and language isn't always aligning into one of these boxes, so we need to think more carefully. So let's take a look at how this can go wrong and how we can be careful to make sure it goes right. So ROC should have defined when I first said this, just area under the receiver operating curve, looking at how well something on our x-axis predicts something on our y-axis. In this case, the x-axis is our uncertainty measure, say perplexity, and our y-axis is whether we're getting something right. This is great, except when we're working with LLMs, it's hard to know, in many cases, whether we're right. So here's a classic example. You ask the LLM, what is the capital of France? And this is a benchmark, so you know the answer. Also, you've probably heard of the answer to this one. The dataset reference answer is Paris. And the LLM says, the capital of France is Paris. And you know that, yeah, that's right. But it's not exactly the reference answer. So what we need is some way of taking all of the possible strings that an LLM can come up with and saying yes or no, do they match the reference answer? So we need some sort of correctness function, right, that's going to take the output, compare it with the reference answer, and give us a thumbs up or a thumbs down. So one thing we can do is look at various measures of word overlap. Okay, so there's a number of these metrics, for example, Rouge-L, that takes your target, takes your prediction, looks at the precision and recall of the overlap, and gives you out a number. Now we don't want a number, we want a thumbs up or a thumbs down. So we're going to pick a threshold and say if it's above that threshold, then it's correct. If it's below that threshold, then it's wrong. As you can see, this isn't perfect, right? Depending on my threshold, I might get this being correct, I might get this being wrong. So we have a noisy classifier. We can also use, for example, LLM as a judge, which is where you take another LLM, ask it, hey, does Paris and the capital of Paris is Paris, the capital of France is Paris, do they mean the same thing? And it'll say yes. Great. Tends to be a bit less noisy, but still a noisy method, especially as you get into longer sentences that may be partially correct or meandering or what have you. So correctness functions can be noisy, and that's not good, because noise in our correctness functions means we're going to have noise in our ROC, which means we're going to have noise in what we think is good. But it's worse than that. They can be systemically biased. Right? So Rouge-L, which is looking at the overlap, is highly correlated with length. Right? The amount of overlap is going to depend on how long your reference answer is. And that's not good. It's worse, though, because our uncertainty quantification metrics will also, in many cases, be biased, right, in a way that matches the bias in the correctness functions. Right? So if you look at sequence probability, which is just summing up the logits or multiplying the probabilities of the tokens, that's going to correlate with length. Longer sentences, less likely it is. So we have a problem that we have both the correctness function on the y-axis and the uncertainty metric on the x-axis correlating heavily with some spurious additional feature, which is going to give us confounding, which is going to systemically bias our findings. It's going to mean certain uncertainty quantification methods look better than they are, other ones look worse than they are because of this uncertainty underlying correlation. So let's look at how this maths in practice. So what we're going to do is we're going to look at our measure of how good our metrics are on the y-axis, and I'm going to look at a bunch of correctness functions on the x-axis. Doesn't really matter what these are. The key thing is the ones over here are ones that are biased with length. Right? So these are all things to do with overlap and things to do with embedding spaces. The ones on the right, still noisy, but less biased towards length. We've got LLM as a judge here. We've got a pure recall version of word overlap. And we've got another LLM-based one in the middle. And we're going to look at a bunch of ways of measuring uncertainty. Again, doesn't really matter what they are, whether you recognize these or not. Just a bunch of methods that we're going to compare. And then we're going to plot the estimated ROC for each of these. So first thing you can see is, yeah, it's really noisy. If you look at sentence burst as your correctness function, you get way different answers than if you looked at Rugel F1. And that's not good. But here, if you look at this top, this is the ordering of the top ones. And you'll see there is a lot of difference in which one wins. Now, when you specifically look at token length or character length, they're basically the same. That's just how long a generation is. That is not typically an uncertainty quantification metric, because, why would it be? But it does correlate with length. Sentence Bird thinks length is great. Very, very good. Other ones think it's less good. Right? So we have not just noisy effects, we have something that is systemically biasing things that correlate with length and making them look good. And this is something that happens in the literature, so there's a lot of works that say, hey, sequence probability is the best way of measuring uncertainty. Sequence probability correlates with length. If you look at Rouge, many of these, it will become top. Meanwhile, if you look at the less biased ones, you still have some noise, you still have some variation, but they're a lot more consistent in what they think is the right order, which is arguably the important. So we can still use analog. We just need to be very careful that we're measuring what we think we're measuring and that we're not letting in additional biases, because we trust a correctness function when it's actually not correctness, it's a proxy. All right, another way of measuring whether a probability or an uncertainty is good is calibration. Right? So here, we're off to a better start. There's a bunch of prior work that says, hey, if you sample from LLMs and take the probabilities by counting, that's actually pretty well calibrated, which is great. That's what we want. But it's also a little bit surprising. Like, we kind of expect a classification model to maybe be well calibrated because it's trained for correctness. LLM is not trained for correctness. It's trained for next token prediction. So we were thinking about this and why would that give you calibration on correctness rather than just calibration on what the next word is? So we've been thinking about this a bunch, and it turns out that you can extrapolate from next token correctness to whether the capital of France is Paris. So there's a bunch of caveats that aren't always true in LLMs. If you take your LLM and you train it with a proper loss, so something like cross-entropy on next token prediction, what we normally do in pre-training or supervised fine-tuning, what we don't do in reinforcement learning, and if the LLM knows what the answer is in advance, so basically this means it's not doing chain of thought. It can't shortcut to the answer if you ask it to, it can shortcut to the answer if you ask it to. Then it's going to be well calibrated. We don't quite have the paper out for this, which is why we're not putting much details here, but it's really cool and I'm very excited about it. But calibration isn't the be-all and end-all. So here's an example of when we might have uncertainty in a model. You've broken your hand, you go to the doctor, you get an X-ray. The model says the probability that this needs cast is 0.5. You're like, well, what does that mean? And since we're all here, we know that if the model is well calibrated, That means if I take all of the x-rays where it was predicted 0.5, half of those will be patients who are prescribed the cast. This is good. It's anchored in reality and it's checkable. It means something. So that's good. But what if you wanted a second opinion, or a third opinion, or a fourth opinion? How would multiple doctors diagnose your x-ray? And here, it's less straightforward. Right? We could have the case where it really is a borderline case. The doctors disagree, there's no consensus. If you ask 4 doctors, they're going to be split on the answer. Right? There's some inherent ambiguity that no one could resolve. Or the model could just be really bad. Right? The doctors could be in 100% agreement of what to do in each case, but the model just put them all in the same bin of I don't know. And you really want to know which of these cases you're in, right? To know whether you should trust your model. So what my colleagues at Apple have done is they've extended this notion of calibration to higher order calibration that looks at moments of ensembles of predictors. So this allows us to decompose in sort of a frequentist analog to the way that we do in Bayesian statistics, the inherent or aleatoric uncertainty from the model-based uncertainty. So this allows us to identify in a testable way which of these situations we're in. All right, so great. It's a little harder than classification, but we can evaluate our measures of uncertainty against some notion of ground truth. But that might not be the only way we want to align. Okay. I might not care about the world outside. I might only care about whether the model can convey what it's thinking. And that's going to be important for, say, safety and interpretability. If the model is making actions based on its own uncertainties, I want to know what that uncertainty was. So, again, as a field, we've decided that the question you ask LLMs about uncertainty is what is the capital of France? I don't know why. I don't think an LLM has ever got this wrong, but we have this shared delusion that sometimes the LLMs do not know what the capital of France is. So we're going to continue with that shared delusion. I ask the LLM, I ask it 10 times, and it gives me a variety of answers. And you know, I could do this every time. But I don't want to, because that's 10 times the cost, and then I need to show the person using ChatGPT 10 different answers, and they need to have the mathematical sophistication to read through these and extract the information. So, sure, I could count them up and say, all right, 8 of these, 6 out of these 8 answers gave Paris, so it's 75% sure it's Paris. Or I could just ask it to give its greedy output, right? And just give me one answer, and most of the time, that's going to be the most likely one. So, you know, fine on average. Better than that, I could ask it, how confident are you? And maybe it could tell me, I'm pretty sure that it's Paris, or I'm 75% sure it's Paris. That would be even better. But arguably even better than that would be if it could say, hey, I'm 75% sure it's Paris, but it could also be Toulouse or Marseille. And the reason I'm 75% sure it's Paris is related to the fact it's the capital and commercial hub. So I could summarize this distribution in a way that contains more information than just a confidence on the most likely answer. So arguably, we're working with language. The natural way to express uncertainty is to use language. It gives us something that can be more flexible than just the most likely or a probability of the most likely, and it's something that people can understand. Problem is, how do we know whether it's worked? It gives us this summary, but if we haven't generated all those samples, I don't know. Is it making this up? Is it hallucinating? We need a measure of seeing whether a summary like this accurately represents the distribution if we were to sample from it, or the distribution if we were to do whatever way of getting generations that the model is using in order to make its decisions. we've been thinking about how to do this. And the line of thought we had is, well, we kind of want our summary to be a sufficient statistic for the distribution. Right? We want it to contain all of the information, just in a nice, small, neat package. So here I'm assuming there is some distribution over answers for the LLM, theta q, so theta is the LLM, q is the query. But I'm never going to be able to look at that, right? It's billions of parameters. I don't really care about its distribution. What I care about is its predictive distribution. What samples is it going to make in future? So I'm going to relax my notion to predictive sufficiency. I'm going to say that for future samples, that could be, but don't have to be, IID samples, an ideal summary would be such that the mutual information between the summary and future samples is the same as the mutual information between a bunch of samples that it's summarizing and future samples. Or alternatively, you can write this as the probability of B given the samples is the same as the probability of B given the summary statistic. And I can relax this a little by sort of Hammersley-Clifford theorem type logic to say this is going to be the same as saying for all words in that generation, words I, the probability of the ith word given the rest of the words and the summary or and the statistic and the samples is going to be the same across all things. So this allows us to go from a thought experiment to a metric by translating this into a closed task. So we're going to say, all right, I'm going to take either my summary or my samples, and I'm going to feed them into a judge LLM. And I'm going to say, hey, judge LLM, here's a task. My task is going to be a new sample, and I'm going to give it everything but one word. And I'm going to ask it to predict that one word. And it's going to give me slightly different distributions depending on whether it's conditioned on a summary or on the samples. But if that's a sufficient statistic for this, they're going to be the same. So I can say I'm going to look at the difference between these two distributions. And it really doesn't matter what measure of difference you look at. We use Wasserstein. It could literally be any distributional distance that you want. And we average that over all B, over all words in B, and that gives us a metric. And this metric tells us loosely how close to being a sufficient statistic a summary is for the samples that it's summarizing. Okay, first off, the good news. Here's the bit where I show a bunch of tables to show that we actually did something rather than just wrote down some math. So compared with what you're going to have to trust me are a bunch of reasonable other things to do in gray, we have better correlation with human judgments of summary quality. And in handcrafted, large scale but handcrafted settings, we are very good at telling a good summary from a bad summary, a good summary from a almost good summary, which is one where we've just left out one of the less likely options, and a number of other ablations of can it tell objectively two different summaries apart. So this is a good way of telling, does my summary string and my bunch of samples contain the same information? The bad news is that LLMs aren't very good at this. Okay, so the reason we had this was because we wanted to be able to assess whether the LLM saying 75% sure it's Paris, but it could be Marseille, and blah, 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 is actually representative of its beliefs. And the bad news is no, it isn't. So what we've got here in this column is we have just taken a bunch of LLMs and got the greedy answer, right? The basic, it's Paris. And we've looked at the self-reflect score, which is our metric between that and a bunch of samples. And you get a number that's kind of meaningless in isolation. Here, we've got what is kind of like the optimal thing, where we get the LLM to generate, I think it's 50 samples, give it those 50 samples, tell it to summarize that, and then look at the difference there. And we get, so the green numbers are better scores. We get better scores from that. That's not surprising, greedy versus sample-based. these two columns are various ways of trying to get the LLM to tell us its uncertainty without generating samples first. And they're basically all worse than just asking it for the most likely one. So even if, so in this chain of thought one, we ask it to enumerate possibilities and then give it its uncertainty, really bad at this. Still really bad if you go for fancy reasoning models that you would assume could be better at this, like DeepSeek, that apparently I can't spell, Quen with questions. Still can't do this any better than just asking for a greedy response. You definitely can't do it as well as conditioning on the summaries, on samples. So that's not good. But in traditional conclusions of your paper 4, we can take this negative result and consider it an opportunity. So arguably it'd be a good thing if we could generate these good summaries. Right? It would allow us to present things to users that are cheap, because we haven't sampled, that are easily digestible, and that are trustworthy. We can't do it yet, but we are optimistic. We're trying to work on this. We hope other people will try and work on this so we don't have to. We think it's an interesting direction. Finally, I want to do the shameless plug part of this talk, where I say, hey, rather than being interested in our research, you should be interested in us. So particularly to those in academia, we have a bunch of collaborations with academic labs. So in the whistle-stop tour today, we talked about collaborations with 3 external labs. We have a lot of interns. There's the work of 7 great interns in this talk. We have a resident program, which is like a postdoc. Unfortunately, none of the papers here have residents, but they're all very good. They just aren't currently interested in uncertainty. And of course, some people decide to give up being a professor and move to industry. 2 of those in this talk. So we are very open to various forms of collaboration with academia. Okay. Thanks.
Questions? Please, Andrew.
Thanks for your talk, I really liked it. So a lot of what makes an uncertainty representation good or not depends on how you want to use it. For example, you could have like a surrogate model in Bayesian optimization that's getting great like marginal test likelihood scores, but isn't very useful for exploring this objective.
Yeah.
So I'm just kind of curious if you thought about some of the downstream applications, like maybe trying to assess the value of data in like making the model more confident.
Yeah, 100%. So when I first wrote this talk, I was writing, I'm going to talk about all the cool stuff people are doing. And when I hit 100 slides, I was like, all right, I got to edit. So initially there was like 3 sections. One was uncertainty quantification, one was applications, and I'm like, all right, this is not going to work. This is a half-hour talk. But absolutely. So some of the stuff that we're doing on Bayesian experimental design really showcases that like the naive thing that you would do, even if it gives consistent probabilities, isn't going to be useful for the task because it doesn't update in the way you're expecting it to update. Right? So there's, I mean, I know you're familiar with all of the like is using context learning Bayesian, etc. And the answer is oscillating. At first it was yes, and now it's no, and I think it's still no. And we find it's no. That if you're doing Bayesian optimization, and you're kind of explicitly saying, hey, I'm thinking this is a Bayesian model, and it's not a Bayesian model, you're going to have trouble. So you need to think of either how do I adjust my model for what this is going to do and how it's going to deal with uncertainties, or find some way of adjusting the uncertainties. So yeah, that doesn't fit in those. It's difficult and nuanced, and it's kind of a lot more, or what we're doing is a lot more specific to application. But yes, absolutely. Calibration and AUROC and stuff are very crude tools for this.
Great, thanks.
Yeah, very nice presentation. My question is this, your self-reflective uncertainty theory is good for textual language-based question. My question in general to Apple is that what it is doing for mathematical questions, mathematical equations problems, because there is no uncertainty there is a right or wrong answer. And a lot of the LLMs, not only Apple, I don't find it mathematically, for mathematical problems, mathematical proofs good enough to.
Yeah. So, yeah, I mean, in that case, so I think there still is value in being able to, so I think there's two questions. One is does it reflect reality? And one is does it reflect what it's actually going to do, right? If it's using under the hood, its uncertainty and its numbers to like move money from your bank account to someone else's bank account, you want to know what it's done in the summary rather than as well as whether that was the right thing to do. So in that case, knowing the difference between it saying, I have definitely sent $50 to Bob, when it actually had a distribution where the most likely number was 50, but the mean was 5,000, and it picked the mean. Totally wrong, not related to reality, but you want to know, do two distributions match? So I think there is, even with math case. But I think for that, the calibration notions make a lot more sense. So with that, and with that, we can get a notion of like, is this likely to be correct, and how likely is this to be correct? Like in one of my totally glossing over a whole bunch of things slide, the unfortunate thing that we find is if the math is hard enough that it needs to think about, you can't trust those numbers. If it's an easy math question, you can trust the numbers. You might not have needed an LLM to get the numbers, but you can trust it, or you can trust its probability. So if you are working with something that is objectively true, then something like this is going to be harder. If you're in the case where you do have some inherent uncertainty, then you get into more wishy-washy notions where calibration maybe isn't the right, or confidence calibration maybe isn't the right thing. I don't know whether, I think I kind of went off on a tangent and answered the question I wanted.
Does Apple AI is working on the LLMs for mathematical proofs and equations, those kind of?
Right, so I need to like caveat that, again, you know what's happening in my little research world of Apple. I do not know what.
Oh, you don't know.
Yeah, I know basically as much as anyone else. And, you know, within machine learning research, we're doing a lot of stuff on reasoning. There's some very cool work, Sami Bengio, Emmanuel Abe Medad, whose last name I'm completely blanking on the reasoning that we can do with mathematics and whether we can trust that. We're currently looking at aligning that with uncertainty, but that's like a twinkle in the eye slide rather than a in-prep slide. The short answer is like people are thinking about this, there's a bunch of Apple papers on reasoning and math, not so much on uncertainty yet.
Please.
So you use LLM as a judge quite a bit, but LLM as a judge suffer from several sort of failure modes,
Yeah.
right? So
Yeah.
did you consider that within your...
Yeah, we absolutely did, and like that. So it's first off, you do get length biases with LLM as a judge, particularly in questions that aren't in benchmarks, right? If you give it a long rambling answer, it tends to be like, yeah, that sounded really smart, I like it. So the length bias totally is a problem. And also there's likely to be other biases coming into play, right, which aren't covered here. So the length bias was the big unknown in the literature one. Like it's very, very overwhelmingly clear with Rougeal. So that's the one we focused on, but this absolutely applies to anything. One of the nice things about being at a big company is we can run human experiments a lot. So looking at how well LLM as a judge correlate with human scores, and in all of the stuff that I've run, it's usually the best thing, but it's never perfect. It tends to be like, treat these numbers with a grain of salt. I'm used to seeing numbers about like 0.8 correlation between humans and 0.7 correlation between LLM as a judge and humans, so it's certainly not perfect. Like really, Because the number one take home of like the first stuff is like don't use Rugel. But the number two thing is like think about what errors your model is making. And yeah, LLM as a judge isn't perfect. You get leakage of information from the model, and yeah, all the problems you said.
Great. We've got a coffee break now. We're going to begin again at 10 to 12. But before we do, let's thank Sinead again.